Do we want to share screen or no? No. It's okay, I think.
Good afternoon, everyone. I'm so glad that you made it last day before the spring break. Right? So it's my pleasure to welcome Professor Barth from UC Riverside. And it's part of the Future City Initiative and Future City Seminar Series. Our department chair, Dr. Kevin Mackey, is also here, so we appreciate his presence as well. Dr. Heeson, he is new faculty in our department, and he graduated from UC Riverside, and his mentor was Professor Barth. So I'll let Dr. Heeson introduce Dr. Barth. I think it's his right.
Okay.
Yeah.
Yeah, thank you for coming. Let me introduce Dr. Barth. Matthew Barth is the Esther Daniel Hayes Distinguished Professor at the Barnes College of Engineering, University of California-Riverside. And he has been named a Fellow of National Academy of Inventors. And he is part of the Intelligent System faculty in Electrical and Computer Engineering and conducts his research at the Center for Environmental Research and Technology, UCR's largest multidisciplinary research center. Dr. Barth's research focuses on intelligent transportation system with the goal of improving environmental sustainability. His current research interest and teaching portfolio includes sustainable transportation, connected automated vehicles, cooperative perception systems, advanced navigation, shared mobility, and vehicle electrifications. Let's invite Dr. Barth for his talk.
All right, well, thank you very much for the great introduction, and it's wonderful to be here. It's always a pleasure to come out and talk about the research that we've done over a number of years. So I've been in the field of intelligent transportation systems now for probably about 3 decades. And so, this all started out about, we encounter all sorts of congestion on the road, and we always hear about crashes on the roadway and how can we improve all these things. And really there's a lot of little things we can do. We can improve the vehicles, we can improve traffic management, but all that falls into this area of what we call intelligent transportation systems. So what I'm going to do today is go through some of the recent research that we've been doing, and then focus primarily on the 2 words up there at the top. One is resilient, and the other one is sustainable. So when we talk about resiliency, I'll say several times, a lot of our solutions are fragile, meaning that if you change traffic volume, they break down and they don't work anymore. So we're going to try to do it in a way where these things are robust, they last under a lot of different conditions, and they're effective. As was mentioned in the introduction, I come from UC Riverside. If you're familiar with California, we're one of 10 campuses, so we're down there in the lower right. So part of the College of Engineering at UC Riverside. And then within our College of Engineering, we have a research center called CSERT. That's the Center for Environmental Research and Technology. And the primary focus of this research center is on transportation, air quality, and energy. And then if you go even further down, we have our Transportation Systems Research Group that Professor Heeson was part of for a number of years. And within that, we focus on these 4 key areas of transportation. Shared mobility, we'll talk a little bit more about that, electrification, and then the fun stuff, which is making them connected and making them automated, right? So everyone's seen and heard about automated vehicles and what they're going to do for society, and we're seeing it with Waymo and everything else. But these are the type of things that we study. I'm also going to talk about this from a smart city perspective. We're very fortunate to have a great partnership with our city of Riverside. It's pretty sizable. It's about 330,000 residents, and very close relationship between the city and the campus, UC Riverside. And so with that, we have a long-term MOU, Memorandum of Understanding, where we can utilize parts of the city as part of our living laboratory. So we have access to traffic signal controllers. We can take our semi-automated vehicles, run them up and down the road. All this is under controlled conditions, but again, we have that working partnership with the city, and we feel very fortunate to have that. A lot of cities don't allow researchers just to go in there and play around with the traffic lights and stuff like that. A few other aspects of what's going on. You know, if you notice in the map, Riverside is.
Sorry to interrupt. I think on Teams we are not sharing the screen on the live seminar. So, so are you here also on Teams?
Yes.
So let's do it here. Yeah, right here. And you're joined here.
So just return, I guess.
Just a second.
Yeah, go ahead.
So I see participants, but not everybody is looking at it.
Or we share screen and on that side. Okay.
No, but when I join,
So we may mute here.
just
Can mute it.
Let's mute this one.
Okay.
there you go.
Okay.
We'll also turn on volume here. Okay.
Test. Does that work?
Jeffrey, can you see now? Tasnia is.
Tesnia says yes.
Okay, perfect.
Okay, to continue. I was about to mention another great feature of City of Riverside is the California Air Resources Board. So if you're not familiar with the California Air Resources Board, very similar to the EPA that puts forth a lot of the rules and regulations when it comes to vehicle, primarily emissions, but also energy and things like that. But the reason I mention that is because they're also a big collaborator with the university, and they are also attracting a lot of other industry and other organizations to the city. So this is not okay. Just to give you an idea, you know, just in the last few years, we've had a lot of new companies move to Riverside, mainly to focus on those things I just mentioned, right? Shared mobility, electrification, connectivity, and automation. Omeo, for example, they make autonomous shuttles.
You're on mute now.
Sorry about that. I think they're not able to.
It's one-way traffic.
Yeah. So what we can do is, can we log out from this one?
Yes, we
just
can.
use this one, right?
Yes.
And that way. Can you confirm if you can see Anne here?
Your microphone's muted.
Yep, all good now.
Okay.
Okay, let me just.
But-
you know,
But here we see nothing on.
here we see nothing.
You want to. You want
Can
to
you
on the-
connect?
You want to also join here?
No, we just need to change the laptop.
Yeah, right. That's laptop. Okay. Just wait here. Wait. Okay. That's the computer. Try the laptop. And
plug in.
I think we have to go to the PowerPoint, right?
We just trying to
Oh, I
duplicate.
see.
That is
Okay, duplicate.
okay. There we go.
Perfect. Online, can you still see and hear us?
Yes, sir, we can.
Perfect.
Okay, finally.
I think they want the big screen though, right?
Yeah.
Move it to share mode.
That's good, right there.
One more setting here for you. Duplicate. Okay.
Okay.
Here we go.
Okay, I'll jump ahead to
Sorry.
where we were. Okay, again, just to summarize, great city to work with, lots of companies coming to work with us, great scenario, great environment for doing smart city research. So because of that, we take a smart city approach. I'm going to get rid of this microphone. Well, we'll just go with it. So we've all heard about smart cities, right? I've heard a lot about it here at University of Central Florida. But the whole idea is to look at our cities and say, let's make this a lot more efficient. Let's make it safer. Let's improve our efficiency overall. You know, and I'll always come back to these key critical things. We always mention safety, mobility, energy efficiency, and things like that. You know, when we come up with new ideas, a lot of these things are so big and major that we can't just simply go to the city, implement it, and then measure it. We often want to test it first, right? And the best way to do that is to create a digital twin, right? Same thing here. I've heard a lot of research already about creating these digital twins. They're very powerful, right? You can make very high fidelity simulations that mimic what's happening in the real world. And that's what I tell all my students. I say, you know, come up with a great idea, implement it in simulation, see how it runs, and then, you know, it's only the best ones after you go through a bunch of iterations to get implemented. So imagine that you're coming up with a new way to time all this traffic signals in the city. You can't just play around with it. You've got to design it first, implement it, prove that it works before you can do a pilot study. And so we use this type of experimental process all the time. Okay, you know, when we look at intelligent transportation systems, you know, you can look at it from different perspectives. One, of course, being vehicle-centric, right? We do a lot of things to our vehicles, right? Our vehicles have evolved quite significantly, right? They're safer, right? We have all sorts of things in it, airbags, anti-lock brake systems, traction control systems, and, you know, now vehicles are starting to communicate with each other. So by sending simple, basic safety messages, right? We have radios on cars that send 10 times a second the state of our vehicle. Other vehicles can listen to that and then make adjustments, right? That has a very high potential for improving safety by avoiding collisions. And then we can also look at ITS from an infrastructure perspective, right? So this is managing traffic. This is where you measure how much flow is there down the arterial roadway, how much volume is on a highway segment. These are all things that we measure, and then we want to manage that too. We manage it through traffic signals, ramp meters, and different things like that. And then lastly, ITS focuses on the traveler, right? So this is where we help travelers figure out what's the best mode to take, what's the best route to take when you're on the roadway system. So there's a lot of ITS-focused things that help the traveler specifically. So the U.S. Department of Transportation, for the last 2 decades, has been developing very specific ITS and more specifically connected and automated vehicle applications. This is a list here. This is actually about 5 years old. There's a website that has all these that explains what all these things mean, right? So if you're looking at a safety application, red light violation warning, these are things that essentially alert drivers about potential drivers that are passing through a red light. There's a lot of mobility type of applications. Some of those you'll recognize, right? So the intelligent traffic signal systems, signal priority, we do that for transit, we do that for freight. And then there's a number of different ones that are focused on energy and the environment, right? We want to do this efficiently. So, one that I'll talk more about a little bit later on is that first one, which is called Eco Approach and Departure at Signalized Intersections. That's giving information to the driver or to the car about what the state of the traffic light is. So as you're approaching the traffic light, you want to know, is it red, yellow, green? Of course you can see it, but you want to know what's the countdown. If you know you have 10 seconds of green left, maybe you want to step on the gas a little bit to get through there, and you want to do that safely. But just having that information is a very simple thing we can do that falls under this connected and automated vehicle application. The problem is we've been designing these for a number of years. Some are very mature, some are just still concepts. But a lot of them are sort of one-offs. We design them for a very static condition, and because of that, anytime you change something, you change the traffic volume, you change how many vehicles have the automation versus ones that don't, the system breaks down. So a lot of these systems are fragile because they're designed very specifically for certain conditions. And so one thing that I'm going to touch on in my talk today is the fact that we need to be flexible with these. We need to look at the parameters of these and adjust them based on a lot of different inputs. And then we're going to do that in a way where we're no longer going to pigeonhole ourselves and say, hey, we're only going to focus on improving safety. We're going to try to do all three of these things. We're going to try to be safe, we're going to try to improve the throughput with mobility, and we're going to try to get an energy benefit as part of that. And so I'll come back to that. The other thing is there's a lot of applications here that require that every single vehicle have the same technology. So you can imagine if you have an automated vehicle or a connected vehicle and it has to talk to the other cars around it, if one of those cars doesn't have that technology, then it's really going to mess up the system, right? It could be where you have a bad actor that's not participating in these cooperative maneuvers. That leads to something that can break down very quickly. So that's the last point there where, again, this can be very fragile because a lot of these applications require that we have 100% buy-in and 100% penetration rate of this automation. And we know for a fact that we're not going to be able to instantaneously get rid of all of our old cars, bring in new cars that have this technology. It's going to be ramped in slowly over time. So I'll just put up this one simulation. This is where if all the vehicles are talking to each other, we don't need signals anymore, right? You can just say, hey, I know where you are, I know where I am, I know what I want to do. You can have these close, paths, trajectories, and you can make it through the intersection as long as everyone is communicating. And this was an area of research about 10 years ago where several different research groups says, hey, this is great. But you can imagine all it takes is one car, one person that says, well, it doesn't have this technology, and you can see what a mess it would be if that person entered this intersection. But again, this provides safe travel as long as everyone's participating. So I was just recently at a conference called the Forum for Intelligent Sustainable Transportation Systems, and I looked at that and I took a video, and this is in Cairo, Egypt. So you can see some of the chaotic activities that you see here where you have a mixture of cars, bicycles, motorcycles, pedestrians, and all this. And it's not too different than what we just saw in that simulation, right? So the way this is being accomplished, this is everyone driving more or less on their own, but you have that coordination, you have that communication. You can't hear the sound, but there's a lot of beeps, right? So that's a basic safety message that they're saying, I'm here, I'm here, I'm here, just so people know where they are and they're not running into each other.
So we have a lot of students from Egypt, I think. So do you identify which city is this?
I see the same thing.
They can hear the sound.
Yeah.
In their mind.
Yeah, and you don't
realized that all these honks mean something. I mean, even different types of honking. It's like, here I am, and sometimes they're mad, sometimes they're not so mad. And anyway, it's an interesting analogy, I think. Okay, let's talk about metrics, right? We want to be able to measure these things. And when we talk about safety, we look for differences of speed between the vehicles. We have a measure called time to collision. If you have two trajectories and you can come close to each other, you want to say, hey, in just 10 milliseconds, you're going to hit each other. So that's something we can measure. Things like queue lengths, spacing, different things, all that corresponds to safety. There's a lot of mobility metrics, right? So this is things you've probably heard: traffic flow, queue length, of cars lining up behind a traffic signal, average speed, vehicle miles traveled, all these things. And this is classically out of your transportation engineering handbook. And then lastly, the environment/energy impacts. We have energy consumption, fuel consumption, pollutant emissions, noise, and different things like that. And if you remember that one chart I showed you from the US DOT, they said, hey, here's a whole bunch of applications that are focused on safety. Here's a number of them that are focused on mobility, and here's on the environment. And what we're going to try to do is look at the benefit, the co-benefits, the synergies, and the trade-offs. So this is your standard Venn diagram where you may have an application that is designed specifically for safety, but it might be at a cost of mobility. And a simple example of that is if you want your roads to be really safe, just separate the cars out, right? Just make them spread out and no one's near each other, and it's really safe. But the problem is that's at the trade-off of mobility, right? Mobility, you want to put in a lot of vehicles and keep them moving at a decent speed, and that's the way you get higher throughput. So there's a natural trade-off to all these different things when we do this analysis. So I had a student look at all these different applications and classify them, which ones fall into the safety area, which ones are in mobility, which ones are in the areas that cross over. And as you would suspect, most of the applications that have been designed, developed, and deployed are primarily focused on safety. Next up would be the mobility ones, and lastly, the energy and environment ones. And not too many, actually, that fall into all three, right? But what I'm going to contend is we can design or redesign all of these applications so that we can change them, right? So if we have one that's focused on safety and one's on mobility, maybe those are combinable to where we can have co-benefits there in that intersection area. So throughout the rest of the talk, I'm going to show different applications and show where that falls within that Venn diagram. And I already mentioned this, right? So if you design an application and you tune it, often we don't change those parameters. We set it up once, and because of that, they tend to break down when things change. Simply changing the volume of traffic can sometimes make these things not work very well. I've heard a lot of pilots that have failed essentially because people haven't programmed in this dynamic calibration aspect, and this is an important thing that we really need to do. Okay, let's go back to that example of what we call eco-approach and departure at a signalized intersection. I already explained it, but imagine that the traffic signal, the traffic controller is broadcasting 10 times a second. Here's the current phase and timing of the traffic intersection. So the idea is cars can then just sit there and listen to that and adjust their speed as they approach the intersection, get through the intersection, and then depart from this. And so what that provides is a greater ability for vehicles to get through the intersection without stopping. So it inherently smooths out the traffic flow as you go through. And then if you have to stop, you can stop smoothly, and there's an energy and emissions benefit for doing that. So this was originally designed to be an energy saver, and it's been proven, right? So it's not just in simulation. This has been deployed in many different cities now. Utah, we have it in Riverside on our main University Avenue. So this is something that actually works. If you have the technology to listen to the traffic lights and then adjust your speed. And humans do this anyway too, right? You're coming up to an intersection, sometimes you look to the side, you see the pedestrian countdown. It's the same exact thing. You're just getting information about what's about to happen with the traffic light. And so if you look at that Venn diagram in the upper right, this is squarely in the environment energy area. There's a lot of variations of this, right? It matters what type of vehicle you drive, whether it's light duty, heavy duty, transit. It's a big difference on whether you're an internal combustion engine versus an electric vehicle. There's different times of signal control timing, right? So fixed time, semi-actuated, fully actuated, whether you as the driver are making the decision or you're letting the automated vehicle make the decision on what speed to travel at. So you can see all the different things that go into this. And that's where I get back to, if you don't set this up correctly, taking into account a lot of these different things, this often falls apart and doesn't work very well. Okay, so that's cars listening to traffic signals and making adjustments to their speed. I put in this slide. So this is our test corridor. This is our UC Riverside campus. This is the downtown area. That's about 6 miles apart. And this is our University Avenue, which is the main linkage between those two. This is where we're able to do our testing. We have access to the traffic signal controllers, a lot of different sensors, right? We put up cameras, we put up LiDAR systems, and that allows us to run our vehicles up and down and make measurements on how much we're doing these improvements in terms of the energy efficiency. So that gives you an idea of that. But in sort of a different way of improving intersections is to have the intersections pay attention to what's going on with the vehicles and then making dynamic changes to the signal timing. So this is possible where, right now what we do is we use loop detectors, right? So we detect vehicles and they say, okay, the vehicle's here. You have a timing scheme that basically says, okay, we're going to go 60 seconds for this direction, and after a 3-second changeover, we're going to go, 40 seconds the other direction. But this concept of dynamic timing has been around for a while. And that's really just if you had perfect state of information of all the traffic coming into the intersection, you can optimize this, right? You just simply come up with a dynamic timing ability to get the most vehicles through that intersection without stopping. So this is also a recent project where there's enough vehicles out there that have, some type of navigation system, right? They all have GPS and they report back position information. From that, and this is from TomTom data, you can figure out pretty quickly where the queue lengths are, how long the typical car has to stop at these different intersections. And so just simply doing an analysis of this real-time travel data, and you can buy a subscription to this. Most cities have enough penetration of the technology that you can figure this out pretty quickly. But the idea is, just as a static review, you can say these signals are not timed very well. You can say, we can improve this by 30, 40% sometimes. And so, we've done that. We've gone to our traffic engineer in the city of Riverside and say, hey, look at this particular intersection. It's poorly timed and we can prove it. And from that, what they can do is they can statically update it once in a while. The way they do it now, they put out loop, tube counters to count the traffic. They do that at different times of the day. But you don't need that hardware. You can just rely on data like this to do this optimal timing. So this is purely focused on improving throughput, which is a mobility measure. So that's why the Venn diagram in the upper right is saying this is a mobility improvement of what we're doing. So we're getting more cars through the intersection without stopping. So then the question is, well, what happens if we do both? And this is the research of one of my graduate students from a number of years ago, where he wanted to do both of those things at once, right? You wanted all the vehicles to do eco approach and departure as you approach the intersection, and you want to do this dynamic timing based on how much traffic and where they are in terms of the intersection. And if you think about it, there's an inherent conflict here, right? So the cars are listening to the intersection, and the intersection is kind of seeing what the cars are doing. And so this is not necessarily co-optimal. You have to have trade-offs in this, but the idea is that you can combine it and get improvements. And the whole point of what I'm going to make here is that we're going to get both a throughput improvement as well as a energy improvement for the vehicles. So I'm going to do this with quadrants. The upper left quadrant is our baseline travel case. This is where cars approach the intersection. You can see the movement through the intersection there. The upper right is the signal optimization. So that's back to the dynamic signal timing. It's paying attention to the cars. This is eco approach and departure here, right? So that's focused on the cars listening. And the combination is what's called eco top, and that's the bottom right over there. And that's just a visualization. If you look at the data, it's this complicated graph. So just to explain it really quickly, if you look at the baseline and you go to eco approach and departure, you get a roughly 12% energy improvement here. But that's at the disbenefit of slowing things down. You have a 7% reduction in mobility. And then if you go left to right on the top, you see that you get a 17% improvement in the throughput and roughly a neutral change to the energy consumption. But if you do both, it's somewhere in between where you get 8% improvement on the throughput and about a 7% improvement on the energy. So this is one case study, a certain volume to capacity ratio, but it just proves that you can tune this, right, and combine these things to get these co-benefits for both of these. The other aspect of this is that you can dynamically tune it. So imagine, I'll turn on my, oops. I sort of lost it here. Okay, if you can see my cursor. So again, eco approach and departure is this star here. That signal optimized one is over here. The thing in the middle is this guy here. So imagine that you're a city and you say, hey, we just had a big event and we want to clear out the cars as much as possible. You can tune all the signals to say maximize mobility and set it there. And then suppose later in the week you have a really bad air quality day. You say, hey, we really want to reduce emissions. You can tune the system to be over here. So you can slide this back and forth, right, and basically tune the system based on these external conditions.
So what data are you changing within the car? Is it the interreliable times or something?
So what you're changing is the parameters of the algorithms, right? So it's how much you want to do your signal phase and timing, and then how much information is you're passing on to the vehicles.
Try and see if I can remove this guy here.
Yeah, I tried to do the pointer, but I didn't see it.
Still there.
That's good.
Good.
It's okay. Okay, we'll keep going.
Which microphone is mute?
Okay, cooperative perception. This is another powerful thing. You know, we're used to looking at the automated vehicles like Waymo. They have cameras, they have LiDAR systems, but more and more research groups, including here at Central Florida, are now putting more sensors on the roadway, on the infrastructure. So cameras, LiDAR on the intersections. And what this does is that it provides additional perception that makes things safer. You can argue that it's also a benefit for mobility, and if you're smoothing out traffic, then that's an environmental benefit too. But then there's a resiliency aspect. This is where, if you're a system in one of these technologies goes out, right? Suppose the automated vehicle has a breakdown, you can still manage things and make this system overall more resilient with a cooperative perception approach. So as part of our corridor that I showed you earlier, we have this intersection. We call this our smart intersection. This is where we took a lot of the latest sensors and mounted them so we can do a lot of these cooperative perception experiments. There's a video, we won't show it today, but if you're curious, it just explains all the different aspects to this overall system. Okay, this is another recent project that talks about emergency response. So if you're in a vehicle and you have an accident where an airbag deploys, then some systems, and this is primarily GM OnStar, it sends a signal out saying, hey, airbag deployed. That can be transferred all the way back to some emergency dispatch center to say, hey, let's respond to this. And there's multiple pathways, right? So if someone observes the crash, they can call 911 and say, hey, there's been a crash, this is the severity, and here's a description. So this is sort of what's going on now. But again, with connected and automation, you can do a lot more. And so one thing we're starting to look at now is, in addition to just simply saying an airbag deploy, you can take maybe the last 10, 15 seconds of data from the vehicle that say, this is what's happened. Maybe you have an inertial sensor and you know that the car rolled over, or maybe you measured the amount of G's in the crash. You can now send information back that's not just a binary signal that says airbag deployed. You can provide a lot of information about what happened to the vehicle. And so that really helps out the emergency response to figure out, should I send a fire truck? Should I send an ambulance? Should I send a lot of blood for blood transfusion? There's a lot of things that make this a lot more robust in terms of how you respond. And you can enhance it even more, right? So if you have that cooperative perception, you can observe things. Maybe this crash happened at an intersection that had cameras or LiDAR. That can be analyzed from a scene perspective and conveyed back to emergency response. You still have observers in 911. What you're doing is you're enhancing how quickly and how well do you respond to these type of safety incidents. And then, yeah, this could be where you could also send out a drone to provide quicker aid than the standard response. Okay, another application. So we all know about routing, right? We drive around, we use Google Maps, Apple Maps, whatever you use. But I'm sure you're familiar where, when we grew up with navigation, we didn't have real-time traffic information. So our decisions on how to get from point A to point B was usually based on the shortest distance. And then now we do have congestion information, so we can now figure out what's the fastest way to get from point A to point B. And then there's been a lot of other variations. One is eco-route. Eco-route basically says, get me from point A to point B with the least amount of energy. And you would think, well, that's probably pretty similar to maybe the fastest route or the shortest distance, but it's different sometimes. It's different because of congestion effects, hills and valleys and different things like that. And you're seeing it now with the Google navigation, where it allows you to take the least energy route. So that's primarily focused on eco routes. So one thing that we've now extended this to is to focus on pollutant exposure. And what we're going to do is we're going to now route things like heavy-duty trucks in a way where the community is exposed at a minimal amount based on how those trucks route themselves. So let's just go through that example. Another thing about many places across the U.S., but particularly where we live in Riverside, is there's warehouses that are popping up everywhere. So these are warehouses that, a bunch of goods come in from the ports. The goods are stored there, they're moved around, and with all those warehouses comes a lot of diesel trucks, right? They have to move these things. A little bit hard to see, but where you see the word legend is the ports of Long Beach and ports of LA, where a lot of the consumer goods come into the US. They get moved throughout the Los Angeles area. Every one of those orange dots on the map is a warehouse that's greater than 100,000 square feet. So you can see in the Riverside area, up in the, if you see my cursor up around here, that's where a lot of warehousing is happening. And again, it's a problem if you have these trucks basically running through our neighborhoods and trying to get to the warehouses and deliver their goods in a certain amount of time. So I'll give you one very concrete example where we did a study. This is the city of San Bernardino. It's more or less surrounded by freeways, right? So we have this 215 freeway here. We have the I-10 that goes through here. And in the middle of that is a airport where Amazon decided to set up an air cargo hub. So you can see the red star with Amazon. So what that means is that you have a lot of heavy-duty trucks coming into the city of San Bernardino trying to get to that red star. And then what we're color coding here is different shades of gray that relates to the population density of the community. So if you have a lot of dark, that means you have a lot of dense housing, neighborhoods, apartments, things like that. And when you come up with something like get me there in the least amount of time or even the shortest distance, it means that a lot of the trucks are routing themselves right through the highest density parts of the city. So you can sort of imagine now, well, why don't we come up with routes that or try to find the areas that have this lower density, right? So we're not, emitting our pollutants in these particular neighborhoods. So that's the crux of this, right? It's called low exposure routing. And just for this one example, by slightly changing these routes of these trucks, we're getting a 28% reduction in pollutant exposure. We're reducing fuel consumption by 5%. But the trade-off, again, you're increasing the travel time by about 13% in this case. So, if you're looking at it from an economic point of view, increasing the amount of time to do your deliveries, that's an economic disbenefit. But from an emissions and a community perspective, it's pretty significant in terms of the pollutant exposure. So again, back to our diagram, if we want the fastest routing, that's sitting squarely here in mobility. If you want eco routing, that's an eco benefit. And then this low exposure is up here on that scale. And same thing, right? You can do this in a way where if you're managing a fleet, you can say, okay, I want you to use your fastest delivery because maybe you're in a time period where you have to meet the nighttime flights, right? So you could advise your fleet to say, use the fastest possible routing. But suppose it's 10 a.m. or 8 a.m. the next morning and you have school kids going to school, you can say, hey, let's route based on the lower exposure case. And then maybe other times you choose this eco case. The point is you can be dynamic in terms of how you route your fleets based on the time of day and what's going on with the conditions in the city. Okay, so now let's talk about resiliency in intelligent transportation systems. So what do we mean by resiliency? Again, do these work under all operating conditions? Can you pick up these ITS applications that we designed for the city of Riverside and come to Orlando? Does it work here? Are they future-proof, right? So if you have one solution today, is it going to work the same way in 10 years from now? And then lastly, we have a lot of bad actors. And this is where we get into cybersecurity, where maybe we're trying to interfere with connected vehicle communications. Maybe we're trying to spoof different signals with GPS. All these things are things that are happening, and so we want our ITS applications to be resilient to that. This is an eye chart. This is basically a chart one of my students made that says what are all the different ways of figuring out how to do vehicle positioning. It's localization. You think about GPS. GPS is a common way of how we do this. GPS is the U.S. constellation of satellites. If you look at all the constellations, including GLONASS and Galileo and all that, we refer to that as global navigation satellite systems. That still provides us with the most positioning solutions that we have today. But you can use inertial measurement units. You can use camera systems, other perception systems. All of that falls into this system here. And the reason I bring this up is suppose that we have GPS jamming. And you think, well, we don't get GPS jamming that much. But if you look at what's going on right now in Israel, Ukraine, all these places, all those places are jammed, right? No one's getting GPS signals, right? Positioning is very difficult to get when they are being jammed and spoofed. And so this is part of it. We want to make our connected and automated vehicles resilient so we don't have that single dependence on figuring out where we are and what we're doing on a simple GPS receiver. So part of this is called resilient positioning or positioning integrity monitoring. And the what integrity monitoring is doing is you're essentially monitoring in real time. What is the accuracy of my position solution? Is the sensor information, is it continuous or is it just intermittent? Are we going underneath a bridge? Is it cutting out at certain times? What sensor information is available? And then the last thing is, can you trust it, right? So if you are being spoofed, do you trust that you think you know where you actually are? All of that falls under the word of integrity. And we do this with airplanes, right? So airplanes are flying around. We need to know where those airplanes are. They have inertial units. They also have the GNSS receivers in order to figure that out. But to determine, are we getting the correct information that's been around in aviation since the 1980s? And surprisingly, we're not doing that with cars, right? We're developing connected and automated cars where if you lose a GPS signal, the thing stops. And this is it's not resilient, right? We want to be able to have integrity monitoring for our vehicles. Okay, so this is one of our projects that we're working with. This is part of the University Transportation Center called Carnations, which is the Center for Assured and Resilient Navigation and Advanced Transportation Systems. But it's really essentially to develop an integrity monitoring system. And just as I said from the beginning, we do a digital twin, which is this, right? You probably recognize the standard things of combining Carla with Sumo. The added things we're doing is we're doing a realistic communication model in S3. We have a higher fidelity GNSS simulator, right? So that's the knowing where the satellites are and what signals are available. And then it also has driver in the loop capabilities. But this is just telling us the environment for developing and testing these things. We'll skip that one. I already mentioned this, where positioning is a key part of all ITS applications, right? So if you lose your position information, these ITS applications break down very quickly. Already mentioned spoofing and jamming. So if you lose those GNSS signals, that's a problem. Okay, so how do you solve this? This is the typical architecture where you combine different kinds of sensors so that if one fails, you can still do a lot of what you intended to do in terms of your automated vehicle. So it's all based around an inertial measurement unit. You can't really mess up an IMU. This is something that just runs by itself and isn't susceptible to outside disturbances. We refer to that as our high rate sensor. and it basically estimates what your vehicle state is, including your position. But then the problem with an IMU is that it drifts, right? So you need to essentially reset it or center it as you move along, and you do that with aiding signals, right? So the typical solution is you use a GPS receiver combined with an IMU, and that gives you a pretty robust positioning system. But as I just mentioned, GNSS can be jammed and spoofed pretty easily these days. So the idea is let's add more things, right? So this is adds communication, so that's the V2X information. You can use LiDAR, you can use camera. All those things are aiding sensors to this overall architecture. And then again, what we're trying to develop is this additional box here, which is the integrity monitoring, where it's a simple concept. If you're making a measurement and all of a sudden one of those estimates from the sensor is wildly wrong, you can detect that here and say, hey, I would not necessarily trust this signal because all of a sudden it's very different than what all the others are predicting. So that's what we mean by integrity monitoring. Okay, so we are implementing this in one of our test vehicles. This is actually our EcoCar electric vehicle that gives us full access to the data from the car, right? We tap into the CAN bus, so we can get things like wheel odometry. We add in our LiDAR and other things. So we get a lot of data from the vehicle, and it allows us to set up this separate system that does the integrity monitoring of the vehicle. So here's the system. Everything in pink here is if you have a GNSS attack, meaning spoofed or jammed, all those things go down, right? And so you're relying then instead on your state estimator. And remember, we're doing that with an inertial navigation unit together with data that comes from the CAN bus and other sensor information. So we've done some tests under real-world jamming and spoofing conditions. And this is tests that happen almost every year. The last one was in 2025. It was called Apex 25. What this is you go out to White Sands test range, and they do purposeful jamming and spoofing of GNSS signals. And it's not just for vehicles, it's for all sorts of applications where for 2 weeks they do these tests and allow you to see how well does your systems work under these conditions. So we sent out 2 vehicles, that have all the different equipment, and we wanted to carry out some simple ITS experiments. Like, how do you platoon 2 vehicles behind each other, right? So that's a common ITS experiment where you're essentially following one car with another, and the whole idea is, does your system fail when all of a sudden you get jammed and spoofed with your positioning? And the answer is, if you design your system well, you can be resilient and still have pretty good positioning, and if it does eventually fail, it fails safe. So there's lots of ways of measuring distances between vehicles. You can take the position of one vehicle, it gets broadcast as a basic safety message back to the other vehicle, so that's a measurement. You can measure it with cameras, you can measure it with radar, you can measure it with LiDAR. So all these are redundant sensors where if you put it together, it allows for that continued positioning when you do lose something like GNSS. So these are just some of the examples of that. The other important point is when you do jamming and spoofing of global navigation satellite systems, you lose the clock. And the clock is important because that synchronizes everything between all the different sensors. So even as soon as you lose the signal, the most important thing often is that clock signal that is used to synchronize all this. So that's another important part of how to be resilient under these conditions. So we went out there this last summer. This was actually in September of last year, where we did these different scenarios. One is intersection experiments, the eco approach and departure, just simple movements through the intersection, and then we did the platooning, as I mentioned already, and got various results. This is asking me if I'm still here. We've analyzed the data and just recently published a paper on this in terms of being able to detect these attack modes and then having this graceful degradation of doing something like a platoon. Okay, so I think, yeah, this is just showing different scenarios where, you know, you're going from that start point in the bottom right and you're going up to the end point in the upper left there. All of a sudden, your GNSS is telling you that you're off where that little triangle is. That's something that you can detect pretty readily and say, okay, I'm now going to depend on something different from my positioning, my relative positioning application. And this is, again, the same case, but we're looking at jamming detection. Okay, so you know, the key thing is that we just started doing this with some pretty straightforward, simple ITS experiments, but the idea is to continue to develop to make these positioning systems more robust and then increase the sophistication of our ITS experiments. So getting into lane maneuvers and different things like that. So we're going to continue this line of research within our University Transportation Center. Okay, so to bring it all together, you know, I mentioned several times, we want to take all these different ITS applications and not just look at aspects of safety separately from mobility, separately from environmental factors. Ideally, we want to combine all those together, and we can do that by putting these applications together. We want them to be dynamically tunable. That makes them that much more robust and usable from a society perspective. And then we want to improve resiliency by, you know, making it so they can respond to a lot of these different disturbances. And the whole area of position integrity monitoring has become much more important now in the whole area of connected and automated vehicles. So with that, I will conclude and just acknowledge a lot of people in the laboratory, a lot of staff and other faculty, and a lot of students that have come through over the years, and a lot of different funding sources, including NSF, RPE, and 2 University Transportation Centers, the NCST, and then Carnations. So I'll finish there and be happy to answer any questions.
Thank you.
Questions? Go on, Dr.
Hi, Fanatik, Transportation Faculty. This is very impressive indeed. Thank you for this presentation. My real question, major question is, how much of that has been applied in the real world other than the university lab work that you showed us, which agencies or real-world agencies have bought into this and actually implemented?
Yeah, it's a great question, and if you look at all these different ITS applications, some of them are deployed. Eco approach and departure is something that many cities now are doing in their cities. Another example is all these fleet routing things. So we've convinced a small fleet in Southern California to start to do this low exposure routing approach. So a lot of them they move from concepts to pilot to full deployment. A lot of pilots out there and a few reasonably fully developed systems at this point.
It would be nice to evaluate the real productivity.
Exactly. Exactly. Yeah. Thank you.
More questions? Go.
So I'm just curious about if you look at the 2 scenarios, the fastest and the eco-top, and you look at the inter-arrival times at an intersection, like what is the distribution? How different are the distributions of inter-arrival times?
Between eco-top and
The fastest, the fast, or what were you saying?
the signal timing one. They're not that too different, quite honestly, right? I mean, where you see is statistically it improves on the order of 5–10%. So you're not seeing too huge of differences of those inter-arrival times. Yeah, I mean, the paper has a lot of those details in it, if you wanted to look at that.
I had a question.
Yeah.
On the CAV. So we have seen a lot of test beds implemented by several DOTs. Like in Florida, we have had several corridors where we installed, RSUs and some test vehicles. So where do you see the connected vehicle going mainstream, and what's for the researchers, who are sitting in this room? Would you say the CAV, especially the connected vehicle, because the autonomous vehicle is still alive, but connected vehicle is becoming saturated research-wise, or there is something more coming there?
I think there is more coming there. This is a common understanding, I think, where if you just simply automate without making the vehicles connected, you're going to get to as good as human drivers, right? Especially when it comes to mobility. If you just simply say, let's put a whole bunch of Waymos and see if traffic improves, it doesn't improve. It gets actually a little bit worse. But the way you can improve traffic with all those is by having them talk to each other and coordinating a lot of their maneuvers. So I think the connected aspect has to stay, and it has to be an important part for the future. And you're right, it used to be a really hot area. It's kind of cooled off a little bit. And I think the idea is to say, let's expand more on the automation side, but connectivity, it has to come back because we need to have that coordination and improvements to mobility.
So a follow-up question on that. So I agree that connectivity is a big part of automation. But then it's when we talk about vehicle to vehicle, connectivity can be leveraged. But when we are talking about V2X or V2I especially, then on the infrastructure side, beyond those test beds and some of the implementations, and you showed an example of adaptive signalized corridor, right? I have an example where a DOT put the signalized intersections, adaptive ones, and after a couple of years they had to take all them down because the benefits were not that much quantifiable, and the nuisance, because the sensors will break down, because all of our algorithms are assuming that we have perfect information of the queue lengths that are forming, the demand which is approaching. But if one of the sensors broke down, I mean, it's a nightmare for them to manage with the red lights flashing, and it's a chaos. So from the practical point of view, those widespread applications of V2I applications, what is the future for that?
Well, I mean, you make a good point about if you're having sensor failures and the whole system falls apart, then obviously you want to design it with redundancy where you can get past that. But it's a difficult question. I think with communication, we're going to continue improving on that and having redundancy to where, I think we'll be able to overcome some of those problems.
Audience, some questions?
I got one question for my devices.
Sure.
So I know we do a lot of experiments and we roll a lot of papers. We are proving our connected vehicle code are very safe and efficient in our very small scale. But for national-wide, we think about the government, think about all the policy. Is it a way to prove or any evidence to show that that thing is really reliable? CLV is really helpful for our society. Do we have a way to do that?
Are you saying, is there a different method of going from simulation to pilot to full deployment?
Yeah, so we don't have like the full deployment in national-wide.
Yeah.
We only do it within in our very small
Right.
experiment.
No, it's a good point. I think we're still mostly in the pilot stage of a lot of these things where, the speed of how quickly we are getting this out there is not extremely fast, right? I guess I'm still hopeful that it will eventually get to that point where they're more widely deployed across larger cities, larger regions, and across the country.
And then I have a follow-up question. So if it's kind of a paradox if we didn't prove that it's very good for the big scale, large city scale, it's safe, it's efficient, how the government would approve us to do that in such a large scale?
Yeah, no, I think this is back to metrics, right? So everything we do as engineers, if we're not showing hard numbers about why this is improved under all cases, under all conditions, then we're not going to convince the government to be able to do this. So, yeah, I mean, we have a lot of projects and we show videos. Hey, look, it's great. Look at the video. But no, we need hard numbers that prove that